Hello, today I'll be talking about Lab 3, the mass of a black hole. The objectives of this laboratory is to find the mass of a black hole using the motion data of a sun moving in an elliptical orbit. The mass of the black hole is 2 times 10 to the 31st. How am I going to find the mass of the black hole? Using the force values I obtained from Python, I will solve for the mass of a black hole using Newton's law of universal gravitation, which will be algebraically manipulated to fit the situation. So let's just go over the principles involved in this lab. There's Newton's first law, which states that an object will remain at rest or at constant motion unless acted upon by a force. Newton's second law, which states that F net is equal to the difference in momentum divided by the difference in time, or simply F net is equal to mass times acceleration. And Newton's third law, which states that an object A will exert a force on object B, and at the same time object B will exert a force on object A, or simply put, FA is equal to negative FB. But most importantly, Newton's law of universal gravitation, which states that the force is equal to the gravitational constant times the first mass times the second mass divided by the distance squared, the magnitude of the distance squared. So let's take a look at Python. Everything is standard apart from the end, which I ran as just the magnitude of the net force, so I could only get that valued. So I could copy it onto Excel, and I would be able to use Excel to calculate the mass of the black hole. I ran it with an indentation, as you see here. However, this is undesirable for this video since it does take quite a while to run, so I will run it without the indentation for simplicity, and it will print out the final magnitude of the net force. And as you see here, it is an elliptical orbit, which means that the force is non-constant. So let's take a look at Excel. So there's these original positions, which I took from star data. And using Excel, I managed to calculate the magnitude of the distance just by squaring this and adding it to the squared y position, and then square rooting that addition. And then I just squared the magnitude of the distance. And then I have the force, which was pulled from Python. As you see here, it's not one, but multiple strings. I did this so I could confirm that the mass of the black hole is consistent and does not change throughout the experiment. Then there's just these constants as the sun's mass and the gravitational constant. Then, since I was using Excel, and first to solve for the Newton's law of universal gravitation, I had to multiply the sun's mass times the gravitational constant and then divide it by the magnitude of the distance square. This is just that value, and then this is divided by the force, the magnitude of the force, and that will give you 2 times 10 to the 31st, which is the mass of the black hole. So I took the liberties to make a couple of graphs. This is distance squared, and this is the magnitude of the force, and we see there is some proportionality to it. As we see, the sun gets closer to the black hole, the force increases drastically. Then as we see it, as the distance increases, the force decreases drastically as such. And we see this, if we were to plot this throughout a much longer time, we would see that it would go up, down, up, down, up, down. Yeah, so that's that. So let's take a look at the physics I used to solve for this lab. So although Newton's law of universal gravitation is important for this lab, since it's all done on Python, I don't really see necessity to cover it. So I'm gonna go over it with what I did on pen and paper, just to make sure I was doing everything right on Excel. So let's see. So Newton's law of universal gravitation states that the force is equal to the gravitational constant times the first mass times the second mass divided by the distance squared. But however, we can't use this since we do not know the second mass or the mass of the black hole. So manipulating it a little bit with algebra, we see that we end up with this statement first. That's the same statement I showed you on Excel, this right here. I'll just show it to you again, this right here. And so we see that, and then we pass it over to the other side of the equals, which means instead of, it's going to be dividing by the F, the magnitude of the force, instead of multiplying. And then doing that, solving for this, we end up with the value of the mass of the black hole, which is 2 times 10 to the 31st. So, what does it mean? How is F-net perpendicular, F-net parallel, and F-net different from delta P over delta T over delta T parallel, and delta T over delta T perpendicular? And it turns out they shouldn't be different, because F-net, as Newton's second law states, is equal to delta P over delta T. Perhaps since we're only taking into consideration that this is with only one force acting, we're obviously not taking into consideration perhaps some electromagnetic fields, but still, for this experiment, F-net is equal to delta P over delta T. So what if our black hole was replaced by a different black hole, but in the same position, and the motion of the observed star is unchanged, and we're assuming that this new black hole has a different mass? How could we tell the difference? And wait, in other words, is it possible for you to find a value for the mass of the new black hole that is different from the mass you found in the original one? And the answer is no, since in Python or whatever, you could have done this on pen and paper as well. Delta P over delta T, or just mass times acceleration, we see that we need to know the acceleration rate. And that rate of acceleration cannot be seen if there is a new one. It cannot be seen if the motion remains unchanged. That would either mean that the sun is orbiting around the same black star or black hole, or that it just or that the black holes have the same mass, and that is that. So if the motion is unchanged, then the mass is either unchanged or well, yeah, it's just unchanged. Thank you.